Good evening, ladies and gentlemen. How is everybody doing this evening? I'm also well, thank you. So I'm assuming you have either a lot of test assignments this week or you don't have a lot. So I think it could be 50-50 for the class at this time, this stage. I can only imagine. So thank you for the usual crowd for being here this evening. I really appreciate it, and I'm happy to see that the usual crowd is attending lectures. And it's like I said, a little bit of admin. And again, I'm preaching at a choir tonight because the people that needs to receive this message are not in class. They do not watch the lecture recordings. And I keep asking stupid question that has been repeated many times on this class, in this module, in lectures. So I've discussed the semester test many times, the format of the semester test also a few times. I've uploaded a practice test for you guys. So remember, the semester test is this week, Friday at 5 o'clock. The test is going to be online. I will make arrangements if there's an issue with load shedding. So that's the first point of admin. The second point of admin, I've scheduled 2 additional classes this week that are not compulsory, so they are free for you to use. And I'm going to use these classes as question and answer sessions for preparation for the test. So the one thing, as I said on ClickUp, both lectures are going to be 7:30 to 8:30 on Wednesday and Thursday night. Unfortunately, I have to move Wednesday night's lecture a bit earlier. So Wednesday night's lecture is going to be 5:30 to 6:30. Thursday night's lecture is going to be 7:30 to 8:30. So you don't have to prepare. So I'm not going to prepare anything for those lectures. So those lectures are open for you. So if you have any questions, then I will answer the questions. If you don't understand anything, then I will help you to understand that. And then in Thursday night's class, I will go through the memo of the mock test. Is that okay with everyone? Okay. Then, if you haven't started your assignment yet, you are in big trouble. Today, I've received a few messages and emails for students that haven't started their assignment yet, and still students asking, they can't see the moon, and they don't know what is going on. They can't find the moon and haven't started yet. How many times in this lecture and lectures and in class have I told you to look at moonrise and set times, determine the appropriate time for all of you to do your observations on? So if you go not submit in on the 31st, then I will subtract 10% per day until you submit your assignments afterwards. Yes, Miss Michaela, I will record both of those sessions and upload it immediately afterwards. Then with that in mind, I will be on campus tomorrow from around about 9:30 to 2:30, and I will be on campus again on Thursday from 9:30 to again 2:30. You're more than welcome to pop in during those times for consultation, or if you need help preparing for the semester tests, then I will be available tomorrow and Thursday. Otherwise, I will also be available virtually. So if those times doesn't work with you, we can set up a virtual consultation as well. Does that sound fair to everyone? So pleasure, guys. So make use of the opportunity. So if you have questions about work or need me to help you with something, explain something, you're more than welcome to pop in tomorrow or Thursday. Otherwise, just send me an email. And it's very easy to set up a virtual consultation as well. If you don't want to speak face to face or don't want to speak virtually, then send me an email. I will gladly help you via email as well. Then lastly, are you all still happy with all the work? Everybody up to date? Okay, cool. And before we start this class, just a bit of advice to everyone. So you are on university level now, not high school level. So on high school, the philosophy of teachers was to spoon feed everyone to make sure they get the appropriate grades and everybody do as well as possible so the teacher look as good as possible. So there, if you fall behind, the teacher will nag you to do your work. There, the teacher will spoon feed you everything. On university level, you are not being spoon fed anymore. Lecturers don't give a crap if you pass the course or not. They are there doing their research, and to teach is one of the extra activities that they need to do, lecturers. So if you fall behind, that's not a lecturer's fault. If you miss communications, that is not a lecturer's fault. If there's a test clash, that is not a lecturer's fault. But if you communicate beforehand, then the lecturers can help you. Then the lecturers will go the extra mile to help you. For this, for example, I'm not obligated to schedule extra classes to help you prepare for the test. But I want you to do as good as possible in the test, and therefore I'm helping you above and beyond what I'm supposed to do. So, for reference sake, please communicate with your lecturers beforehand. If you receive your test dates in the first 2 weeks of a semester, make sure there's no clashes. Contact your lecturer, then that can be sorted out easily. But letting a lecturer know there's a clash a few days before you write, then that becomes an impossible task to fix. And also, I know some of you are shy and some of you don't really like to introduce you to your lecturers, but introduce yourself to your lecturers, start networking. In the future, that will help you a lot. In the future, you'll see a lot of your work opportunities and opportunities in the future will depend on who you know. And by introducing yourself to your lecturers, then you know your students know your lecturers, and then they can help you. A couple of months back, a previous student of mine approached me for a recommendation letter for a bursary. So I've gladly written him a recommendation letter. But I received an email from the committee, and one of the committee members deciding on the bursaries knows me personally and contacted me and asked me, how well do I know the student? Is the student a good candidate for a bursary? And therefore, I can say, yes, I know the student very well and is a very good candidate. So it all depends on what you want to do with your future. So try and engage with your lecturers. But enough preaching for tonight. I know I'm preaching at a wrong group. You guys are always in class. The people that needs the preaching are not attending classes, not watching lecture recordings. Also, keep in mind for your other courses, us lecturers has the ability on ClickUp to see who of our students has downloaded the material, looked at the material, how many times you've downloaded it, how many times you've looked at the material. And also the recording, if you download your recordings from Blackboard itself, we have the functionality there as well. And it's quite shocking to see the majority of the class do not engage on ClickUp at all. So keep that in mind. And then we're going to start this lecture tonight with meteoroids, asteroids, and comets. So what can you guys tell me about meteorites, asteroids, and comets? Yes, Armageddon and Deep Impact are two very cool sci-fi movies. Really fast rocks and ice. So I'm glad to see there are a few sci-fi fans out here that watched classic sci-fi movie shots such as Armageddon and Deep Impact. So they killed the dinosaurs, correct? People keep calling them shooting stars. We'll discuss why they are called shooting stars. Some meteors created by planets, moon collisions, yes. So for tonight's lecture, comet has an ice tail when it's close to the sun, yes. So in this lecture tonight, we are going to look at meteoroids, meteors, meteorites, asteroids, comets, and asteroid and comet impacts. From this photo, can you determine what this is? So yes, this is a meteorite. And how can you determine it's a meteorite? So this is where geologists comes in, but usually when you see pieces of a rock that is melted like this, that gives us two clues. One, it has a very high iron content or iron-like content. So it could be derivatives of iron, it could be nickel, could be iron mixed with other heavy elements. So the majority will be iron. That's why you can see it's a bit melted. And due to the friction of the atmosphere, the iron has melted. So yes, you're correct. That's what looks like space metal. So this is one thing to determine it's a meteorite or asteroid. And second thing is if you put a magnet to it, it will have a small magnetic field and is a bit magnetic due to the high iron content. So these are a few of the bigger asteroids in our solar system. So here we can see the diameters and specifications of these asteroids. So here we can see Rosetta visited this asteroid in 2010, and its dimensions is 132 by 110 by 76 kilometers. So that is one big rock. And that is why, like I said in previous lectures, why big mining companies are actually now investigating asteroid mining. So how cool would it be if a mining company set up a mining facility on one of these asteroids? And you mine the asteroids for rare metals such as iron, gold, silver, nickel, and you bring it back to Earth. Is there anything to mine on the moon? Unfortunately, not on the moon. So the moon doesn't have really precious metals, but the asteroid belt and some asteroids have some really extreme metals that you can make some money off. So that is why mining companies are now investigating how to do asteroid mining. And in the near future, that is going to become a reality. As you look at NASA's Artemis mission that's coming up, around about 2030, NASA's planning to go back to the moon. Elon Musk with SpaceX is planning to go to the moon. And then after the moon, he wants to go to Mars. So if you go to Mars, then you're almost at the asteroid belt. So it's only a matter of time before it really becomes a reality. And can you recognize this image? So yes, you guys are correct. This is a typical comet. And you can see this by the tail. So question, do you think Mars is also on the roster for the mining company? So yes, it will be. So the one thing is, to prove of concept, you need someone to first create a settlement on Mars. So the first settlement will only be traveling one direction, but after that, as soon as there is a way to leave Mars again, then yes, mining companies will start to mine Mars as well. First, I need to determine if there are any precious metals on Mars or precious minerals. But yes, that is also a good possibility that might happen in the future as well. In chapter 15, you began your study of planetary astronomy by considering evidence about how our solar system formed. In the 3 chapters that followed, you surveyed the planets and found more clues about the origin of the solar system, but also learned that most traces of the early histories of the planets have been erased by geological activity or other processes. Now you can study smaller, less altered objects that tell more about the era of planet building. Asteroids and comets are unevolved objects, leftover planet construction bricks. You will find them much as they were when they formed 4.6 billion years ago. Meteors and meteorites are fragments of comets and asteroids that arrive at Earth and can give you a close look at those ancient planetesimals. As you explore, you will find answers to 4 important questions. Firstly, where do meteors and meteorites come from? What are asteroids? What are comets? And what happens when asteroids and comets hit Earth and other planets? So, comment, I like how we are just talking about mining Mars as if Martians won't have a problem. Nice. So, yes, that is one thing. So, speaking about, so that's going to be the last lecture for the semester. It's going to be the possibility of life on other worlds and in the universe. But if we look at Mars, there are a few possibilities. Either there are no life on Mars and we can mine it. Second possibility is there were life on Mars, and by mining we might find fossil records of the life on Mars. Or the last possibility, life on Mars might be underground, because Mars doesn't have an ozone layer and as a volatile surface, so you can actually be safe underground. So yes, those are some interesting questions. Then, do you think that minerals mined from other planets would be at a higher price than mined from Earth, even if they are the same mineral or material? That is a really good question. So first we have to answer why certain materials expensive. Think about gold. So gold is expensive because it is a rarer metal on Earth. You will find more normal iron than you find gold. So gold is a rare metal, and therefore it has a high commodity value on it. But say, for example, hypothetical, if we go to the asteroid belt, we have a asteroid that is 90% gold, and we find a way to bring that asteroid back to Earth and then mine it on Earth. Then there will be an abundance of gold, and that will drive down the gold price. So the price of these metals depends on how rare they are. So if you have more gold, then the price will go down. If you have less gold, then the price will go up. Then is it possible to find new elements on asteroids? Yes, that is possible. So the elements we have discovered them on Earth and in space. And a few of them as man-made elements that we created in laboratories. But yes, There could be a new element out there that we haven't discovered yet. So while diamonds are quite common, but their price is inflated by restricting demand, it's possible that space mining companies would simply refuse to sell too far below Earth's market rate. That could also be. So that all depends on what our people in finances will do about it. So prices might even decline, and so the industry might lose its worth a bit. Yes, that can happen. So if we find minerals on Mars, there's possibility that we can advance Mars on life at a quicker rate. That is also possible. Then I wonder when there will be a new element on a periodic table. So that can happen. So if you Google it, you'll see there's actually a few elements that's been man-made, created on Earth. One afternoon in 1954, while Miss E. Hewlett Hodges from Sailor, how did you pronounce that? Salagua, Alabama. So Alabama basically lay napping on a living room couch. An explosion and sharp pain jolted her awake. Analysis of the brick-sized rock that slammed through a ceiling and bruised her left leg showed that it was a meteorite. Mrs. Hodges is the only person known to have been injured by a meteorite. Coincidentally, she lived right across the street from the Comet Drive-In Theater. Meteorites arrive from space all over Earth every day, although not as spectacularly as the one that struck Miss Hodges. You will learn in this chapter that meteorites are fragments of asteroids, and that asteroids, as well as their icy cousins, the comets, carry precious clues about the conditions in a solar nebula from which the sun and planets formed. Because you cannot easily visit comets and asteroids, you can begin by learning about the pieces of those bodies that come to you. So when an asteroid hits the Martian surface, some of the particles kick up, reach escape velocity, and can travel to Earth. Yes, that has happened a few times in the past. You learned some things about meteorites in Chapter 15, Section 2, when you studied evidence for the age of the solar system. There you saw that a solar system includes small particles called meteoroids. Some of them collide with Earth's atmosphere at speeds of 10 to 70 kilometers per second. Friction with the air heats the meteoroids enough so that they glow, and you see them vaporize as streaks across the night sky. Those streaks are called meteors or shooting stars. And something interesting about these meteors or shooting stars is the color at which they burn in the atmosphere. So the friction causes heat, so heat causes them to burn, depends on what elements they are carrying or consists of, because so if you burn certain elements, the flame will have a certain color. So that's just something interesting. If a meteoroid is big enough and holds together well enough, it can survive its plunge through the atmosphere and reach Earth's surface. Once the object strikes Earth's surface, it's called a meteorite. So, ite being the Greek root for rock. As you will learn later in this chapter, the largest of those objects can blast out craters on Earth's surface. But such big impacts are extremely rare. The great majority of meteoroids are too small to form craters. What can meteorites and meteors tell you about the origin of the solar system? To answer that question, you can consider their compositions and their orbits. So, can you guys tell me what are the two biggest impact craters in South Africa? So yes, the biggest one in South Africa is the Vredefort crater, on Afrikaans the Vredefort Koepel. So yes, it is basically on the edge of the Free State. So it starts at Parys and it continues into the Free State. So that is quite big. And then another one is just north of Pretoria called the Tshwine crater. So let me just type it into the chat how you. So these are the two largest impact craters in South Africa, and you can actually visit those two. One of the best places to look for meteorites turns out to be certain parts of Antarctica. The nearest Earth rocks are buried under miles of ice, so any rock you find there must have fallen from space. The slow flow of the Antarctic ice cap toward the ocean concentrates meteorites in areas where the moving ice runs into mountain barriers, slows down, and evaporates. Teams of scientists travel to Antarctica and ride snowmobiles in systematic sweeps across the ice each southern hemisphere summer to recover meteorites. After 25 years of work, more than half of the 40,000 meteorites in humanity's possession are from Antarctica. So, something interesting. Do you guys know that South Africa participates in the Arctic Research Base? And you guys also know that South Africa has one of the best research vessels in the world. So yes, Ms. Kutsia, you are correct. SA Ugalas, or the SAS Ugalas. So the SAS, just the acronym for South African ships, so the SAS Ugalas, and then we have the SAS Ugalas 2. So we have two research vessels, and they are some of the best research vessels in the world, especially the Ugalas 2, because it's state of the art. So each year, the South African National Space Agency, or SANSA for short, opens up applications for a crew to go man the Arctic base for a year. So you usually need to have your qualification. You need to have a BSc of some kind or a BEng of some kind, even a master's preferably. Then you do then you contact them, you do the application form, and then you are invited for a series of tests. But remember, you're going to be a year in Antarctica. So for Antarctica, you need to be mentally in the right place to see if you won't mentally break down. So you have to go through psychological tests, and then you also need to go through a physical test to make sure that you are healthy enough for the work and Antarctica. Then it's about, on the SAS Ugalas, it's about a 3 to 4 month journey to Antarctica. So you go there in the summer when the ice is a bit thinner. Then they drop you off, then you travel to the research base, then you spend a year at the research base. Then after a year, the SAS Ugalas comes and pick you up again. Then it's about 3 to 4 month journey back to South Africa. So that is very, very cool. And then there's also, between South Africa and Antarctica, there's also an island, Marion Island. And you can actually do volunteer work, or not volunteer work, get paid for it. You can go and work on the Marion Island Research Base as well. So that is something, if you're interested in those kind of things, that you can apply for in the future. They usually open up applications each year around about August. And then they leave for the Arctic or Antarctica in end of January the following year. So would you want to join the Agulhas? So I would enjoy the research work, but for me that is a bit too long to be away from my family. And then, sir, have you ever seen the waters in the Drake Passage? So no, I have not. So Antarctica is apparently a pretty cool place. So in this image, we can see braving bitter cold and high wind teams of scientists riding snowmobiles search for meteorites that fell long ago in Antarctica and are exposed as the ice evaporates. When a meteorite is found, it is photographed where it lies, assigned a number, and placed in an airtight bag. In image B, thousands of meteorites have been collected in this way, including rare meteorites from the Moon and Mars. Meteorites can be divided into three broad composition categories. Iron meteorites are solid chunks of iron and nickel. Stony iron meteorites are mixtures of iron and stone. And stony meteorites are silicate masses that resemble earth rocks. Carbonaceous chondrites are a special type of stony object. Here we can see the different types of meteorites. The main types of meteorites have distinctive characteristics. In image A, an iron meteorite, actually composed mostly of a mixture of iron and nickel. In image B, an iron meteorite's Whitman-Starton crystal pattern shows that this material cooled very slowly from a molten state and must once have been inside a fairly large object. C, a stony iron meteorite. D, a stony meteorite. And in E, a carbonaceous chondrite. Meteorites are a rare type of stony meteorite that is rich in carbon, making the rock very dark. Iron meteorites make up only 6% of meteorites witnessed falling from the sky. So you can estimate that Can everyone hear me? Apologies about that. It took me a bit longer to reconnect, but now we can continue. Iron meteorites make up only 6% of meteorites witnessed falling from the sky. So you can estimate that only about 6% of meteoroids traveling through space near Earth have iron composition. You might wonder, why do iron meteorites make up 66% of meteorites found in the ground? Because iron meteorites don't look like ordinary rocks. They are easy to recognize because they are heavy, dense lumps of metal. If you trip over one on a hike, you are more likely to recognize it as something odd, carry it home and show it to the local museum. Also, some stony meteorites deteriorate rapidly when exposed to weather. Ions are made of stronger material and generally survive longer. The recognizable and durability of iron meteorites means there is a selection effect that makes it more likely they will be found than other types of meteorites. So, sir, how does a meteorite come to exist? So we will learn about that momentarily. When iron meteorites are sliced open, polished, and etched with acid, they reveal regular bands called Wittmann-Stratum patterns, caused by alloys of iron and nickel that formed crystals as the molten metal cooled and solidified. The size and shape of the bands indicate that the molten metal cooled very slowly, indicating a location inside bodies at least 30 kilometers in diameter. In comparison, a small lump of molten metal exposed in space would cool in just a few hours. On the other hand, the iron meteorites do not show effects of the very high pressures that would exist deep inside a planet. Evidently, iron meteorite material formed in the cooling interiors of planetesimal-sized objects, smaller than planets. This is one important clue to the origins of meteorites. In contrast to ions and stony ions, stony meteorites are common among meteorites seen falling to Earth. Although there are many different types of stony meteorites, you can classify them into two main categories depending on their physical properties and chemical content: chondrites and achondrites. Who of you have ever seen a meteorite, or the layman's term a shooting star? Never. They're actually very quite common. So usually in city areas. So if you are in Johannesburg or Pretoria or in Gauteng, you should be able to see roughly 4 meteorites an hour. So it's actually quite common. If you are in darker places, then that can go up to about 12 to 15 an hour. So if you are bored one night and want to see a meteorite, just take a pillow and a blanket or a sleeping bag and go outside and just go lay on the grass and look up. Just stare up in the night sky. And you should be able to see one. So you should be able to see 4 per hour in really light blue places. But yes, you can actually see them. So, sir, hear me out on this. It's too cold nowadays to be outside. So when it's so cold, then you especially need to be outside. With the cold, the atmosphere is a lot more stable. So that is why most astronomers love cold nights because the atmosphere is stable and you can do much better observing. So usually if you are an amateur astronomer and you have your own telescope, the best time to do observing is the night exactly after a cold front. Then the atmosphere will be at its most stable. Chondrites look like dark grey granular rocks. In general, chondrites contain some volatiles, including water and organic carbon compounds. A few chondrites evidently formed in the presence of liquid water. Most types of chondrites also contain chondrules, small round bits of glassy rock, only a few millimeters across, to be glassy rather than crystalline. The chondrules must have cooled from a molten state quickly, within a few hours. One hypothesis is that chondrules are bits of matter from the inner part of the solar nebula, near the Sun, that were blown outward by winds or jets to cooler parts of the nebula, where they condensed and were later incorporated into larger rocks. Another hypothesis is that the chondrules were once solid bits of matter that were melted by shock waves, spreading through the solar nebula and then re-solidified. It's a weird question, but what happens to an asteroid after impact? Especially if it's like, for example, everything can't explode, can it? So yes, it depends on the size of the asteroid and the material is made of. So usually it will vaporize on impact or just above impact. And depending on the size, you can still find pieces when it hits the ground, but the majority of times it will vaporize. Yes, achondrites are the opposite of chondrites. Among the chondrites, the carbonaceous chondrites are a rare but quite important subtype. These dark grey rocky meteorites are especially rich in water, other volatiles and organic compounds. Those substances all would have been lost if the meteorite had been heated even to room temperature. Many carbonaceous chondrites also contain small, irregular inclusions rich in calcium, aluminium, and titanium, called CAIs for calcium aluminium rich inclusions. These bits of matter are highly refractory. That is, they vaporize or condense only at very high temperatures. If you could scoop out a portion of the sun's photosphere and cool it, the first particles to solidify would have the chemical composition of CIAs. As the temperature fell, other materials would become solid in accord with the condensation sequence described in Chapter 15, Section 3. When a cooling blob of solar composition material finally reached room temperature, you would find that almost all the hydrogen, helium, and some other gases, such as argon and neon, had escaped, and that the remaining lump would have almost exactly the same overall composition as the main mass of carbonaceous chondrite. Carbonaceous chondrite meteorites are evidently very old samples of the solar nebula, confirmed by the fact that CAIs have radioactive ages equal to the oldest of any other solar material. The chondrites show properties ranging from carbonaceous chondrites, most of which have avoided being heated or modified, to other chondrites in which the material was slightly heated and somewhat altered from the form in which it first solidified. Chondrites in general offer us the best direct information about conditions and processes occurring in the earliest days of the solar nebula when planetesimals and planets were forming. So a bit off topic, but what is the smallest size a white dwarf can be? That I don't know by heart, but let me quickly see if I can find it for you. So if I'm looking at my material, the smallest white dwarfs is roughly about 2,000, it's a radius of about 2,000 kilometers. So yes, that would be odd, 2,100 miles, so of 2,000 kilometers in radius. Unlike the various types of chondrites, the stony meteorites called achondrites contain no chondrules and also lack volatiles. These rocks appear to have been subjected to intense heat that melted the chondrules and completely drove off the volatiles, resulting in a composition similar to the Earth's basalts. The different types of meteorites evidently had a wide variety of histories. Carbonaceous chondrites are like unaltered lumps of condensed solar nebula. Achondrites seem like pieces of lava flows, where the stony iron and iron meteorites apparently were once deep inside the molten interiors of differentiated objects. Meteorites provide evidence that a young solar system was a complicated place. A typical meteoroid has roughly the mass of a paperclip and vaporizes at an altitude of about 80 kilometers above Earth's surface. So when you look up in the night sky and you see those 4 meteorites per hour, they are usually these small meteorites or meteoroids. They're usually the size of a grain of rice, and they usually vaporize in Earth's atmosphere. So the meteor trail points back along the path of the meteoroid. So if you study the direction and speed of meteors, you can get clues to their orbits in the solar system before they encountered Earth. So at the Hartbeespoort Duke Observatory, we have a meteoroid and meteorite tracking system. So it's a camera system that looks at the sky, and if a meteorite passes over, it tracks its trajectory. So from the trajectory, we can determine where it came from and where it is going. So if we can detect it's above a certain size, then we might be able to track where it fell, and we can go and try and find the piece that fell to the ground. But usually most of them burn out. So yes, we have a tracking system for meteorites. So one way to backtrack meteor trails is to observe meteor showers. On any clear night, you can see 3 to 15 meteors per hour. But on some nights, you can see a shower of hundreds of meteors per hour that are obviously related to each other, seeming to come from a single area of the sky called the radiant of the shower. Who of you guys have seen a meteor shower before? So there are actually 2 prominent meteor showers each year that you can observe. The one is around about March, April, and the other one is around about August, and that is when we move through the tail of a comet. So that is something spectacular to see every year. Meteor showers are named after the constellation from which they seem to radiate. For example, the Perseid shower, seen in mid-August, radiates from the constellation Perseus. The fact that the meteors in a shower appear to come from a single point in the sky means that the meteoroids were actually traveling through space along parallel paths. You see their fiery tracks through Earth's atmosphere in perspective, so they appear to come from a single radiant point, just as parallel railroad tracks seem to come from a single point on the horizon. So why are weather anchors called meteorologists when they don't tell us anything about meteors? That is a very good question. In image A, meteors in a meteor shower enter Earth's atmosphere along parallel paths, but perspective makes them appear to diverge from a single point in the sky. Image B, similarly, parallel railroad tracks appear to diverge from a point on the horizon. Then image C, meteors in a shower are debris left behind as a comet's icy nucleus evaporates. The rocky and metallic bits of matter spread along the comet's orbit. If Earth passes through such material, you can see a meteor shower. The meteoroids in a meteor shower are understood to be dust and debris released from the icy nucleus of a comet. When Earth passes through the stream of material, you see a meteor shower. In some cases, the comet has wasted away and is no longer visible. But in other cases, the comet is still prominent, although located somewhere else along its orbit. For example, each May, Earth comes near the orbit of Comet Halley, and you can see the Eta Aquarid shower. Each October, Earth passes near the other side of the orbit of Comet Halley, and the Orionid shower appears. So these are the two I was talking about, and you can see that each year. Even when there's no shower, you still can occasionally see meteors that are called sporadic meteors because they are not part of specific showers. Studied of the trails of sporadic meteors reveal that they have a dual source. Many come from comets, as do meteors in showers, but a few come from the asteroid belt. Objects that are big and durable enough to become meteoroids on the ground seem always to come from the asteroid belt. The physical characteristics of meteorites provide evidence that they are fragments of parent bodies in the asteroid belt that were large enough to grow hot from radioactive decay or other processes. They then melted and differentiated to form nickel, iron-nickel cores, and rocky mantles. The molten iron cores would have been well insulated by the thick rocky mantles, so that the iron would have cooled slowly enough to produce big crystals that result in Wiedemann-Staten patterns. Some stony meteorites that have been strongly heated appear instead to have come from the mantles or surfaces of such bodies. Stony iron meteorites apparently came from boundaries between stony mantles and iron cores. Collisions could break up such differentiated bodies and produce different kinds of meteorites. In contrast, chondrites are probably fragments of smaller bodies that never melted, and carbonaceous chondrites may be from unaltered bodies that formed especially far from the Sun. In this image, we can see a large planetesimal can keep its internal heat long enough to differentiate. Collisions break up the layers of differentiated composition. Meteoroids formed near the surface are rocky. Meteorites from the deeper in the planetesimal were heated to high temperatures. Fragments from near the core might have been melted entirely. Fragments of the iron core can fall to Earth as iron meteorites. Now we're going to talk a bit about asteroids. Asteroids are distant objects too small to study in detail with Earth-based telescopes. Astronomers nevertheless have learned a surprising amount about those little worlds using spacecraft and space telescopes. Evidence from meteorites showed that asteroids are the last remains of the rocky planetesimals that built the terrestrial planets 4.6 billion years ago. Notice 4 important points and 3 new terms. Most asteroids are irregular in shape and battered by impact cratering. Many asteroids seem to be rubble piles of broken fragments. Then second, some asteroids are double objects or have small moons in orbit around them. This is further evidence that asteroids have suffered collisions. Thirdly, a few asteroids show signs of geological activity that probably happened on their surfaces when those asteroids were young. Then lastly, asteroids can be classified by their albedos, colors, and spectra to reveal clues to their composition. This also allows them to be compared to meteorites and labs on Earth. C-type, S-type, and N-type asteroids are the main classes discovered by this method. The first asteroid was discovered in 1801 by the Sicilian monk Giuseppe Piazzi and later named Ceres. Astronomers were excited by Piazzi's discovery because Ceres orbits about 2.8 AU from the Sun in a wide gap between Mars and Jupiter, where it was thought a planet ought to be. But Ceres has less than 1/4 diameter of Earth's moon, much smaller than any of the planets. 3 even smaller objects, Pallas, Juno, and Vesta, were discovered within a few years, all orbiting between Mars and Jupiter. So astronomers decided Ceres and other asteroids should not be considered true planets. You learn in Chapter 18, Section 6 that Ceres, the largest object in the asteroid belt, has now been reclassified as a dwarf planet because it has enough gravitational strength to squeeze itself into a spherical shape, but not enough to have swept up or cleared away the rest of the asteroids. Today, more than 400,000 asteroids have well-charted orbits. Other than the dwarf planet Ceres, only 3 are larger than 400 kilometers diameter. Most are much smaller. There are probably 1 million or more that are larger than 1 kilometer in diameter. Astronomers are sure that all the large asteroids in the asteroid belt have been discovered, but are also sure that many small asteroids remain undiscovered. Movies and TVs have created a common misconception that flying through an asteroid belt is a hair-raising plunge requiring constant dodging left and right. The asteroid belt between Mars and Jupiter is actually mostly empty space. In fact, if you were standing on an asteroid, there would be many months or years between sightings of other asteroids. You don't have to go all the way to the asteroid belt if you want to visit an asteroid. Some follow orbits that cross the orbits of the terrestrial planets and come near Earth. Others wander far away among the Jovian worlds. There are also asteroids that share orbits with the planets. Several research teams are now intent on identifying near-Earth objects, or NEOs, which could potentially hit Earth. The most dangerous type of NEOs, those with orbits that cross Earth's orbit, are called Apollo objects, after the first such asteroid discovered. The combination searches are estimated to have found at least 93% of the Apollos and other NEOs larger than 1 kilometer in diameter, and are now focused on finding a similar percentage of objects down to about the size of 150 meters. In March 2009, NEO searchers spotted a small asteroid 2 to 3 meters in diameter, about the size of a small truck, on a collision course with Earth. The astronomers were able to observe it in space before impact and discovered that its color and albedo matched the type of asteroid found mostly in the outer belt. The asteroid entered Earth's atmosphere over the deserts of the northern Sudan and exploded. Scientists from the United States and Sudan searched for pieces of the object. This diagram plots the position of known asteroids between the Sun and the orbit of Jupiter on a specific day. Most asteroids are in the main belt. Squares filled or empty show the location of known comets. Although asteroids and comets are small bodies and lie far apart, there are a great many of them in the inner solar system. So here we can actually track, and then it's important to track them to find these Apollo objects to make sure that we don't have a extinction level event on Earth, such as the dinosaurs, or if an asteroid is on a collision curve, that it then cause major havoc in one of our cities, and then we have time to respond. And that is why a couple of months ago, NASA had the DART mission, where they are experimenting to see if they can deflect an asteroid. So deflecting an asteroid is to push it a little bit. So not push, so merely to either speed up the asteroid or slow it down. And that causes this orbit to change. So in this image, we can see the main belt asteroids lie between orbits of Mars and Jupiter. Asteroids that could approach Earth are shown in red. Then Trojan asteroids orbit in two clouds 60 degrees ahead of Jupiter and 60 degrees behind. And something interesting about Jupiter is protecting us from most asteroid strikes. Because besides the Sun, then Jupiter has the second largest gravitational pull in the solar system. So that means Jupiter is protecting us from possible threats. But if we miss some of these threats, then we need to find a way to neutralize them. So in this image, we can see search team leader Mouashad left of the Faculty of Physics and Sciences at the University of Khartoum, and meteor astronomer Peter Jenniskens right of the Carl Sagan Center at the SETI Institute pose with one of the first fragments found of the small asteroids that exploded over the Sudanese desert in March 2009. So they found about 4 kilograms of fragments corresponding to a rare type of stony meteorite. For the first time, a definite connection could be made between an asteroid observed in space and meteorites with properties measured in Earth laboratories. In 2010, the Japanese probe Hayabusa returned a capsule to Earth containing a few tiny grains from the surface of the S-type asteroid Itokawa, which were found to be chemically identical to one of the most common types of ordinary chondrite meteorites. There are other non-belt asteroids behind the main belt. Gravitational effects of Jupiter and the Sun combine to trap two groups of asteroids in the Lagrange points that are 60 degrees ahead and 60 degrees behind the planet in its orbit. These are called Trojan asteroids because individual objects have been named after the heroes of the Trojan War. Astronomers have also found a few objects in the Lagrange points of the orbits of Mars and Neptune. Question: so would it be possible to try and pull off a real-life Armageddon on an asteroid on a collision course with Earth? Yes, so that is why we need to study these or track these objects. So if we detect one that's on a collision course to Earth, the best possibility if we detect it a while beforehand, then we can change the trajectory of the asteroids. And one way to do it, you send a rocket to it, and use the rocket to either speed up the asteroid so that will miss Earth, or you slow it down and it will miss Earth. Or the other thing is you can blow it up, but if you blow it up, then the fragments might still collide with Earth. The object Chiron, found in 1977, is about 170 kilometers in diameter. Its orbit carries it from the orbit of Uranus to just inside the orbit of Saturn. Objects like Chiron with orbits between or crossing orbits of the Jovian planets are called centaurs. Although it was first classified as an asteroid, Chiron later surprised astronomers by suddenly releasing jets of vapor and dust. You will learn in the next section that this more resembles the characteristics of comets than asteroids. Centaurs showed that the distinction between asteroids and comets is not clear-cut. As technology allows astronomers to detect smaller and more distant objects, they are learning that our solar system contains large numbers of these small bodies. The challenge is to explain the origin. So question: could we prepare for impact and possibly survive? Yes, we can. So that is why it is important to track these objects so we can prepare for it. And I don't know if you guys know, but we are due for another extinction level event. So if you look at Earth's past and you look at the statistics of these events, may I'm speaking under correction, but there is about 5 extinction level events in the past, where one is the dinosaurs. So if you look at the statistics, then we are about 100,000 years overdue for a extinction level event. So this far, our existence are just based on luck. So I thought, so an old hypothesis proposed that asteroids are the remains of a planet that exploded. Planet-shattering death rays may make for exciting science fiction movies, but in reality, planets do not explode. The gravitational field of a planet holds the mass together so tightly that completely disturbing the planet would take tremendous energy. In addition, the present-day total mass of the asteroids is located only about 1 in 20 of the mass of Earth's moon, hardly enough to be the remains of a planet. So look back to the figure that opens chapter 15 to see an extrasolar planetary system with an asteroid belt interior to the orbit of the Jovian planet. That arrangement may have the same cause in our solar system. Astronomers have evidence that asteroids are the remains of material laying 2 to 4 AU from a sun that was unable to form a planet because of the gravitational influence of Jupiter, the next planet outward. Over the 4.6 billion year history of the solar system, most of the objects originally in the asteroid belt have collided, fragmented, and been covered with craters. Some asteroids were perturbed by the gravity of Jupiter and other planets into orbit that collided with planets or the Sun, caused them to be captured as planetary satellites, or ejected them from the solar system. The present-day asteroids are understood to be a very minor remnant of the original mass in that zone. Even though most of the planetesimals originally in the main belt have been lost or destroyed, the objects left behind carry clues to their origin in the albedos and spectroscopic colors. For example, C-type asteroids have albedos less than 0.06 and would look very dark to our eyes. They are probably made of carbon-rich material similar to the carbonaceous chondrite meteorites. C-type asteroids are more common in the outer asteroid belt. It is cooler there, and the condensation sequence predicts that carbonaceous material would form there more easily than in the inner belt. The second largest asteroid, Vesta, has solidified silicate lava on its surface. Ceres, 950 kilometers in diameter, is almost twice as big as Vesta, but its surface is ice-rich carbonaceous material. Herschel Space Telescope observations of Ceres revealed water vapor venting from 2 regions on its surface. The Dawn spacecraft arrived at Ceres in 2015, imaging occasional haze in a large crater that may be one of the water vapor sources. The differences between the 2 largest asteroids offer a real puzzle for planetary scientists. So yes, Ceres is reclassified as a dwarf planet. So here we can see 2 images of Ceres and Vesta. In image A, the image of the asteroid Vesta, made from a distance of 2,700 kilometers by NASA's Dawn spacecraft, shows Vesta's south polar region, which is dominated by the Rhelasylva impact basin. Then image B, dwarf planet Ceres, the largest object in the asteroid belt between Mars and Jupiter. The prominent white spots may be salt deposits left by evaporating water. So that means Pluto is also just an asteroid? Not. So Pluto is also classified as a dwarf planet. Although there are still mysteries to solve, you can understand the story of the asteroids. They are fragments of planetesimals, some of which differentiated, developed molten metal cores, in a few cases even had lava flows on their surfaces, and then cooled slowly. The largest asteroids astronomers see today may be nearly unbroken examples of original planetesimals, but the smaller asteroids are fragments produced by 4.6 billion years of collisions. Now we can start talking about comets. So is the difference between dwarf planets and asteroids just the size and mass? So yes, the difference there is the size, mass, and they are round. So that means they have enough mass to create a round surface or round look. So yes, Ceres is the closest dwarf planet. So do you know asteroid Oumuamua? Yes, I know about Oumuamua. So Oumuamua is the Hawaiian word for visitor. So that is the first extrasolar object that we discovered, observed, and meaning extrasolar, it came from outside the solar system and passed through our solar system and is now exit our solar system and deep space again. So I'm not completely sure where Oumuamua comes from. I'm not an expert on asteroids or Oumuamua, but Oumuamua came from deep space, entered our solar system, and then moved through our solar system and exited again. Few sights in astronomy are more beautiful than a bright comet hanging in the night sky. It is a common misconception that comets whiz rapidly across the sky like meteors. Actually, a comet's motion is hardly apparent. Night by night, its position shifts slightly against the background stars, and it may remain visible for months. While everyone can enjoy the beauty of comets, astronomers study them because they are messengers from the past, carrying cargoes of information about the origin of our solar system. In this image, we can see Comet McNugget swept through the inner solar system in 2007. And was a dramatic sight in the southern sky. Seen here from Australia, the comet was on its way back into deep space after making its closest approach to the Sun 10 days earlier. Comet McNugget began this passage with a period of about 300,000 years. Gravitational perturbations by the planets changed its orbit shape from elliptical to hyperbolic. So it will never return, but instead it's leaving the solar system to journey forever in interstellar space. So interesting physics, where does it get the kinetic energy to travel this fast? So yes, if you can get escape velocity from your solar system, then it is possible. So one thing is you can Google it. So there's the intergalactic gravity highway. So that is the fast with less gravity in our solar system, and we actually use that to send probes to the outer solar system and to different planets. And what's meant by that is we can do slingshot maneuvers around planets. So for example, the probes on the way to Jupiter usually does a slingshot maneuver around Mars. So that means you're on an angle in Mars. So you get pulled by the gravitational field of Mars, but you're not caught by the gravitational field. So that means the gravitational field is actually accelerating you and slingshotting you around a planet, and then you gain momentum and kinetic energy. And if you do a couple of slingshot maneuvers around different planets, then yes, you can retrieve escape velocity and leave the solar system. So yes, we use slingshot maneuvers to get probes to the Jovian planets and also into deep space, such as Voyagers. So what are the properties of comets? As always, you should begin your study of a new kind of object by summarizing its observational properties. What do comets look like and how do they behave? So yes, Mr. Melville, you're correct. They are very cool physics, and another word for it is gravity assist, as you can call it. I like to call them slingshots, but yes, gravity assist is a synonym for it. Or like Interstellar, but that was the event horizon of a black hole. Yes, you can also do a slingshot or gravity assist around a black hole as well. As long as you have an object with a higher gravitational field, then you can do a slingshot maneuver. So notice three important properties of comets plus three new terms. Comets have two kinds of tails, shaped by the solar wind and solar radiation. Gas and dust released by a comet's icy nucleus produces a head or a coma, and are then blown outward away from the sun. The gas produces a gas tail, and dust produces a separate dust tail. Secondly, comet dust produces not only one of two types of comet tails, but also spreads throughout the solar system. Some of those comet dust particles later encounter the Earth and are seen as meteors. Then lastly, evidence shows that some comet nuclei are fragile and can break into pieces. So what is the geology of comet nuclei? As always, you should begin your study of nuclei. Is this the same as the previous slide? Yes, it is. The nuclei of comets are quite small and cannot be studied in detail using Earth-based telescopes. Nevertheless, when a comet nucleus approaches the Sun, it emits material that forms into a coma, so the head, and a tail that can be millions of kilometers in size and easily observed. Spectra of comet, or comae, the plural of coma, and tails indicate that nuclei must contain ices of water and other volatile compounds such as carbon dioxide, carbon monoxide, methane, ammonia, and so on. These are the kinds of compounds that would have condensed in cold regions of the solar nebula. This convinces astronomers that comets are ancient samples of the gases and dust from which the outer planets formed. As the ices absorb energy from sunlight, they sublime change from a solid directly into a gas. The gases break down and also combine chemically, producing other substances found in comet spectra. For example, vast clouds of hydrogen gas observed around the heads of comets are understood to derive from the breakup of ice molecules. Five spacecraft flew past the nucleus of Comet Halley when it visited the inner solar system between 1985 and 1986. Other spacecraft flew past the nuclei of Comet Borley in 2001, Comet Wild in 2004, Comet Tempel 1 in 2005, and Comet Hartley 2 in 2010. Images show that all these comet nuclei are 1 kilometers to 10 kilometers across. Similar in size to many asteroids and also irregular in shape. In general, these nuclei are darker than a lump of coal, which suggests composition similar to carbon-rich carbonaceous chondrite meteorites described earlier in this chapter. The mass and density of comet nuclei can be calculated from a gravitational influence on passing spacecraft. Comet nuclei appear to have densities between 0.1 and 0.25 grams per cubic centimeters, much less than a density of ice. Also, as you will learn later in this chapter, comets subjected to tidal stresses from Jupiter or the Sun come apart very easily. Comet nuclei have been described as dirty snowballs or icy mudballs, but it seems to be incorrect. Their shapes, low densities, and lack of material strength suggest that comets are not solid objects. The evidence leads astronomers to conclude that most comet nuclei must be fluffy mixtures of ices and dust with significant amounts of empty space. On the other hand, images of the nucleus of Comet Wild 2 reveals cliffs, pinnacles, and other features that show the material has enough strength to stand against the weak gravity of the comet. Here we can see the nucleus of Comet Halley is irregular and emitting jets from active regions. Here we can see debris ejected from the nucleus. Here we can see the nucleus of Comet Wild 2 is highly irregular. Nucleus of Comet Hartley 2, jets visible in the right end. Then here we can see active regions on the nucleus of Comet Borley emits jets when they are rotating into the Sun. And here is nucleus of Comet, I don't know how to pronounce this, but it looks like Russian. So these are all wavelength images made by the Hubble Space Telescope and from passing spacecraft show how the nuclei of comets produce jets of gases from regions where sunlight vaporizes ices. This looks like I accidentally copied this slide. So this is a sentence that continues. So the evidence leads astronomers to conclude that most comet nuclei must be fluffy mixtures of ices and dust with significant amounts of empty space. On the other hand, images of the nucleus of Comet Wild 2 reveal cliffs, pinnacles, and other features that show the material has enough strength to stand against the weak gravity of the comet. The nuclei of comets appear to have a crust of rocky dust left behind as the ices vaporize. Breaks in that crust can expose ices to sunlight, and vents can occur in those regions. It also seems that some comets have large pockets of volatiles buried below the crust. When one of those pockets is exposed and begins to vaporize, the comet can suffer a dramatic outburst, as Comet Holmes did in 2007. The Stardust spacecraft flew through Comet Wild's 2 tail in 2004, collected dust ejected from Comet's nucleus, and returned samples to Earth for analysis. In 2005, Deep Impact released a probe that collided with Comet Tempel 1 at 10 kilometers per second. The probe broke through the comet's crust and blasted vapor and dust into space, allowing Deep Impact plus space telescopes and observatories on Earth to analyze it. Stardust and Deep Impact data revealed the surprising fact that some comet dust is crystalline and must have formed originally in warm locations near the Sun, but then somehow was included in comet nuclei in a cold outer solar system. The Rosetta spacecraft began orbiting the nucleus of comet, I don't know how to pronounce that, in 2014, dropping a probe, Philae, which landed and returned data and images from the surface. Rosetta and Philae detected organic molecules such as methanol and formaldehyde emanating from the comet's surface. So here we can see images from the Rosetta spacecraft of a portion of the comet's nucleus. So the red ellipse is the red ellipse with dimensions of 16 by 160 meters marks the likely location of Philae lander determined by Rosetta's CONSERT radar experiments. Then in image B, view of the comet's surface from Philae showing small cliff or large boulder approximately 4 meters tall. Directly in front of the probe, the end of one of the lander's 3 landing legs can be seen in the foreground. Family relationships among the comets can give you clues to their origin. Most comets have long elliptical orbits with periods greater than 200 years and are known as long period comets. The long period comets' orbits are randomly inclined to the plane of the solar system, so those comets approach the inner solar system from all directions. Long period comets revolve around the Sun in about equal numbers in prograde orbits, the same direction in which the planets move, and retrograde orbits. In contrast, about 100 or so of the 600 well-studied comets have orbits with periods less than 200 years. The short period comets usually follow orbits that lie within 30 degrees of the plane of the solar system, and most revolve around the Sun prograde. Comet Halley, with a period of 76 years, is an unusual short period comet with a retrograde orbit. So why do you think there are so many more asteroids on one side of the solar system than the other? That is most likely due to Jupiter that captures asteroids, but that usually shifts as Jupiter orbits around the Sun. A comet cannot survive long in an orbit that brings it into the inner solar system. The heat of the sun vaporizes millions of tons of ices during each passage and reduces comets to inactive bodies of rock and dust. Such comets can last at most 100 to 1,000 orbits around the sun. The astronomers calculated even before a comet completely vaporizes from solar heating, it can't survive more than about 500,000 years crossing the orbits of the planets, especially Jupiter, without having its path rerouted into the sun or out of the solar system or colliding with one of the planets. Therefore, comets visible in our skies now can't have survived in their present orbits for 4.6 billion years since the formation of the solar system. And that means there must be a continuous supply of new comets. Where do they come from? In the 1950s, astronomer Jan Oort proposed that long-period comets are objects that fall inward from what has become known as the Oort cloud, a spherical cloud of icy bodies that extends from about 10,000 to 100,000 AU from the Sun. Astronomers hypothesized that the Oort cloud objects were originally planetesimals formed in the outer solar system that were tossed to their current distant locations by the gravitational influence of the growing Jovian worlds. The Oort cloud is estimated to contain several trillion icy bodies. Far from the Sun, they are very cold, lack comae and tails, and are invisible from Earth. Astronomers calculated some Oort cloud objects can be perturbed by the gravitational influence of passing stars, so that they fall into the inner solar system. There, the heat of the Sun warms their ices and transforms them into comets. The fact that long-period comets are observed to fall inward from all directions is explained by the Oort cloud reservoir being spherically distributed around the Sun and in a solar system. A few short-period comets, including Comet Halley, also seems to have originated as long-period comets from the Oort cloud, but then had their orbits altered by a close encounter with Jupiter. However, that process can't explain all the short-period comets. The Kuiper belt, which you first encountered in Chapter 15, Section 2, when you initially survey the solar system, is another source for icy bodies passing through the inner solar system. Kuiper belt objects orbit in the same direction as the planets and in the plane of the solar system. Mathematical models show that it is likely for a Kuiper belt object, perturbed inward by the influence of the giant planets, to move into an orbit resembling those of short-lived comets. Comets vary in brightness and orbit. Nevertheless, there are two basic types of comets in our solar system. Some originate in the Oort cloud, far from the Sun. Others come from the Kuiper belt, just beyond Neptune. They all share one characteristic. They are ancient icy bodies that were born within the solar system and was young. Most meteors are small particles ranging from a few centimeters down to microscopic dust. Astronomers estimate that Earth gains about 40,000 tons of mass per year from meteorites of all sizes. Did you guys actually realize that we gain 40,000 tons per year due to meteorites hitting Earth? That may seem like a lot, but it's less than 100,000th of a trillionth of Earth's total mass. Statistical calculations indicate that a meteorite large enough to cause some damage, like the one that hit Mrs. Hodges in a house in 1954, strikes a building somewhere in the world about once every 16 months. Declassified data from military satellites show that Earth is hit about once a week by meteor-sized meteors. What happens when even larger solar system objects collide with Earth? So what do you guys think? That is damage. Barrington crater near Flagstaff, Arizona is 1.2 kilometers in diameter and 170 meters deep. Eugene Shoemaker proved in his 1963 doctoral thesis that a crater must be the result of an impact rather than a volcanic eruption because quartz crystals in and around it have been subjected to pressure much higher than can be produced by a volcano. Further study shows that Barringer crater was created approximately 50,000 years ago by a meteorite estimated to have been about 50 meters in diameter, as large as a good-sized building. That hit at a speed of 11 kilometers per second, releasing as much energy as a large thermonuclear bomb. An object of that size could be called either a large meteoroid or a small asteroid. Debris at the site shows that the impactor was composed of iron. So here we can see the image A, the Beringer meteorite crater, is nearly a mile in diameter and was formed 50,000 years ago by impact of an iron meteorite estimated to have been roughly 50 meters in diameter. So notice the raised deformed rock layers in all around the crater. The brick museum building visible on the far rim at the right proves some idea of scale. Then in image B, like all large impact features, the Beringer meteorite crater has raised rim and scattered ejecta. On a summer morning in 1908, reindeer herders and homesteaders in central Siberia were startled to see a brilliant blue-white fireball brighter than the sun streak across the sky. Still descending, it exploded with a blinding flash and an intense pulse of heat. The blast was heard up to 1,000 kilometers away, and the resulting air pressure circled Earth twice. When members of a scientific expedition arrived at the site in 1927, they found that the blast had occurred above the stony Tunguska River valley and had knocked down trees pointing away from the center of the region about 30 kilometers in radius. In this image, we can see in 1908 the Tunguska event in Siberia destroyed an area the size of a large city. Here the area of destruction is superimposed on a map of Washington, D.C. and its surrounding beltway. In the central area, trees were burned. In the outer area, trees were blown down in a pattern away from the path of the impactor. No crater has been found at the Tunguska site, so it seems that an explosion, estimated to have equaled 12 megatons of TNT, occurred at least a few kilometers above ground. A detailed analysis of the available evidence suggests that the impactor's speed and direction resembled the orbit of an Apollo object. Astronomers produced computer models of objects entering Earth's atmosphere and concluded that the most likely candidate for the Tunguska object is a stony asteroid about 30 meters in diameter, perhaps 1/10 the mass of the Beringer impactor. An object of this size and material strength would have fragmented and exploded at just about the right height to produce the observed blast. The conclusion is consistent with modern studies of the Tunguska area, showing that the thousands of tons of powdered material with a composition resembling carbonaceous chondrites was scattered in the soil. There are some very big craters in the solar system, for example on the Moon, that show what can happen when a full-size asteroid or comet collides with a planet. Also, Earthlings watched in awe in 1994 as fragments from the nucleus of comet Shoemaker-Levy 9 slammed into Jupiter with a series of explosions equaling millions of megatons, that is, trillions of tons of TNT. The impacts left scars larger than Earth visible on Jupiter's cloud tops for months afterwards. In 2009, another object, it was not observed prior to the impact, left a single blemish on Jupiter that was easily observed from Earth. Evidently, impacts large enough to significantly affect a giant planet like Jupiter happen impressively often. So another one that you can see actually YouTube videos of was around about in 2012, where there was another large impact in Russia. So here we can see fragments of a comet falling towards Jupiter. Here we can see at visual wavelength the impacts of these objects. And if we look through a radio telescope at the infrared part, we can actually see where these impacts of was in Jupiter's atmosphere of Shoemaker-Levy 9. What would happen if an object the size of Shoemaker-Levy 9 or even larger were to hit Earth? 65 million years ago, at the end of the Cretaceous period, over 75% of the species on Earth, including dinosaurs, became extinct. Scientists have found a thin layer of clay all over the world that was laid down at a time, and it is rich in the element iridium, common in meteorites but rare in Earth's crust. This suggests that an impact occurred that was large enough to have altered Earth's climate and caused the worldwide extinction. Geologists have located a crater at least 180 kilometers in diameter centered near the village of Chicxulub in northern Yucatan region of Mexico. Although the crater is now completely covered by sediments, mineral samples show that it contains shocked quartz crystals of impact sites and that it is the right age. The impact of an object 10 to 15 kilometers in diameter formed the crater about 65 million years ago, just when the dinosaurs and many other species died out. Scientists now conclude that this is the scar of the impact that ended the Cretaceous period. The giant impact scar buried in Earth's crust near the village, here we can see it, in the northern Yucatan Peninsula, was formed about 65 million years ago by the impact of a large asteroid or comet. In image B, this gravity map shows the extent of the crater and surrounding region of disturbed crust hidden below limestone deposits long after the impact. There are a number of major extinctions in the fossil records, and at least some of these were probably caused by large impacts. Large asteroid impacts on Earth happen very rarely from a human perspective, but they happen often relative to geological and astronomical timescales. For example, astronomers estimate an Apollo object hits Earth once every 250,000 years on average. A typical Apollo with a diameter of 1 kilometer would strike with the power of a 100,000 megaton bomb and dig a crater more than 10 kilometers in diameter. Astronomers estimate that there are about 1,000 Apollos 1 kilometers in size or larger. And the good news is that none of them are known to be on track to hit Earth in the foreseeable future. The bad news is that not all of these dangerous Apollo objects have been found yet. A significant danger lies to the more common smaller yet still substantial meteorites, which are difficult to detect with current telescopes. For example, an asteroid designated 367943 Duend, estimated to have been 30 meters in diameter, about the same size as the Tunguska impact that passed only 27,700 kilometers from Earth's surface in February 2013. That is closer than humanity's geosynchronous communication and weather satellites. A very near miss indeed, yet it was discovered only a year earlier. The future of our civilization on Earth may depend on our doing an increasingly careful job of tracking both large and small objects that cross our path with surprising frequency. And that, ladies and gentlemen, is tonight's lecture on asteroids, comets, and meteorites. Do you guys have any questions? So if you guys have no more questions, you are more than welcome to log off. I will be on campus tomorrow if you want to pop in for consultation or ask questions about the exam. I will also be available virtually if you rather want to see me virtually. Then tomorrow night we are going to discuss the last chapter of this module, and that will be on extraterrestrial life. And then, yes, on Thursday night, we are going to go through the mock tests. So I want you guys to prepare and go through the mock test, and then we can discuss the different answers. So should you be afraid of being hit by an asteroid? No, you don't need to be afraid. So if you're not going to attend tomorrow's lecture, that is not a problem at all. So if you guys have no further questions, you are more than welcome to log off. I will remain active for another minute or two if you have questions. Otherwise, have a wonderful evening and good luck with everything happening for the rest of the week. Yes, so I have a undergraduate degree in computer science. So I did my undergrad in electrical engineering, and I did another undergrad in computer science. And then after that, a master's in astronomy. So you missed a bit of admin course connection issues. So yes, the mock test is still available on ClickUp. So we'll go through the mock test on Thursday evening. So Thursday evening, I scheduled a class that's not compulsory from 7:30 p.m. to 8:30 p.m. So that's also going to be a question and answer session. And I've scheduled another question and answer class on Wednesday that is not compulsory. That will be from 5:30 to 6:30 if you have any questions. It's a pleasure. So if you guys have no further questions, then I'm also going to log off. So have a wonderful evening, and I will see you guys tomorrow. Good night, everyone.